for the equation of motion, we need to apply the equation of motion in the tangential direction, since it involves the restoring force. So note the negative sign. So I need to complete this equation. So this direction is the positive direction for the acceleration. So we have sigma force. Okay, sigma force at the direction perpendicular. I mean, in direction of the motion of the pendulum. Okay. And also for the sigma force, we can obtain that, which is equal to mg sine theta. Okay, so that is the only component involved in the system for in the direction of the motion of the pendulum. Okay, so note the negative sign right here. Okay, so why negative? Because it is against the direction of the motion, right? Now we go to the kinematics. We need to consider the kinematics. So again, I need to complete this equation. Okay, so we know that the acceleration is equal to the displacement, but second order of the displacement, which is double. We need to differentiate displacement twice to get the acceleration, and S may be related to theta by the equation, this one. So we can replace everything and change them in theta instead of S, because we in the pendulum, the motion of the pendulum is it's better to use theta angle instead of the displacement. So we can also, since displacement is equal to I theta, I is the moment of this is L actually. L is equal to the length of the chord. So acceleration is equal to this formula, L theta double dot. Alright. So again, I need to complete this equation. So we put everything to the side. We put this one inside here. Okay. And then we divide everything with m. So m is eliminated. So right here also we can eliminate the m. So this is the outcome after we rearrange the equation. Okay, and we replace the acceleration. The solution of this equation involves the use of elliptic integral. Okay, so elliptic integral, you don't have to worry about that. Okay, you can Google that to understand more. For small displacements, so we use this a lot. We use assumption for small displacement. Sine theta is equal to theta. Okay, in which case theta double dot plus g theta. So from here we replace this one with this one. Okay, sine theta is equal to theta. So you need to know this assumption. Sometimes we use cos, sometimes we use sine. I will tell you about this later on. So this is the first formula that you can use. When the displacement is small, sine theta is equal to theta. Okay, this is to simplify our equation. If the question mentioned that the displacement is small, therefore we can use this assumption. But there is no mentioning about the small displacement, we cannot use this assumption. Okay. Now we can compare this equation with the standard equation, which is this one. Okay. So we replace the x with theta. So theta double dot plus omega n square theta equal to 0. So when we compare with this one, you can see the relation, the equation for natural frequency. So natural frequency is equal to this formula, right? The period of time required for the ball to make one complete swing is therefore. Now we can calculate the period. We can use the formula given previously. Okay, so from here we can calculate the period. If the value of L and G is given, G is the gravity, so we can calculate the value of period of the pendulum. Now we go to the next example. In example 2, the problem is different, and we are going to consider moment. Okay, the 10 kilogram rectangular plate shown in is suspended at its center for a rod from a rod having torsional stiffness. So this rod has torsional stiffness 1.5 Newton per time meter over radian. Okay. Determine the okay. So Newton meter is this one. This I mean this one is torque. It has a similar unit with torque, and the stiffness, torsional stiffness, we divide by radian, because it is in rotational motion. Rotational motion. Determine the natural period of vibration of the plate when it is given a small angular displacement. So again, it mentions small angular displacement theta in the plane of the plate. So it will rotate like this. Now again, we need to consider the free body diagram. Since the plate is displaced in its own plane, the torsional restoring moment created by the rod is so we need to know this formula. This is like Hooke's law, F equal to kx, but it is in circular or rotary motion. But it is an oscillation. So this plate will vibrate like this. Okay, this moment acts in the direction opposite to the angular displacement theta. Okay, why? Okay, let we consider. We look from the top. So when we look from the top, this is the rectangular plate, and then when it's small, there is small displacement. For example, like this. So there is angle right here, theta. So this theta is small. So it's move to the right side before we release it and before it's oscillate. Okay. So the moment is since we pull, if you look at here is anti-clockwise, so the moment will be clockwise. The moment will be clockwise. So is in the opposite direction to the theta. Again, the angular acceleration acts in the direction of positive theta. So this you need to always remember this. Now we can go to the equation of motion. So I will complete this equation. We consider the moment, the total moment, and then we have acceleration, and this is the moment of inertia. Instead of a mass, when we are considering rotational motion, we will use a moment of inertia. Okay, and we can replace this one with the formula that we know, which is m equal to k theta. So that is the similar like Hooke's law. So for the right hand side, the acceleration, we can replace it with the actually this is not the acceleration in the direction in the linear direction, but this is the acceleration for circular motion. So that's why we replace it with theta double dot. Right. So I complete this equation. So when I replace or I rearrange this one, so I can get this formula. Since this equation is in the standard form, again remember the standard differential equation form, the natural frequency is, so this is the related to the natural frequency, which is this is equal to omega n square. So we can get that omega n is equal to sert k over I o, right? Similar to this one. The moment of inertia of the plate about an axis coincident with the rod is given by. So we can calculate the moment of inertia. So we have the formula for rectangular shape. We also have other formula for different kind of shape, such as circular, square, even a complex shape. We can also calculate the moment of inertia for complex shape. Alright. So for rectangular shape, we can use this formula. IO is equal to 1 over 12 m a square plus b square. What is a and what is b is the width and the length of the plate, and m is the weight. which is 10 kilogram. If I'm not mistaken, I go back to the example. So we have 10 kilogram right here. So this is the width and this is the length, right? We put the value inside here, and I forgot to put, okay, there is a bracket right here, so we can get this value for the moment of inertia. Now we can calculate the tau, the period. So I complete this equation first. It's like a puzzle. After I finish this equation, then you can understand. Alright, so we can use, I forgot this one. Okay, we can use this formula, and we can replace the angular, the natural frequency, and then finally we can get the period. Alright, now we've finished. I think we have finished with the example 2. Now we go straight to the example 3. Okay, hopefully you are ready. Now I read the question. The bent rod had a negligible mass. So this one, the mass is 0, so we don't have to consider the mass. And it supports a 5 kilogram collar. So this one, this is the collar at its end. Determine the natural period. Again, the question asks us to find the natural period, or the period. Natural period is related to the natural frequency. Okay, natural period for the system. Alright. So you need to consider all parameter given here. Alright. Again, the first thing you need to do is diagram, free body diagram and kinetic diagram. So for the free body diagram, it's right here. Kinetic diagram is right here. And we need to draw the free body diagram with an angle. Okay, it doesn't matter if you want to push the bend rod upward or downward. It will be the same. So it doesn't matter. But usually what you will want to do is you want to stretch or extend the spring. Spring is right here. Spring is right here. So you want to extend the spring. So it depends. If you want to compress, it also can. So, but in this case, we extend the spring. Okay, and we will have angle theta. Alright. So the motion of the the motion of the bend rod is in circular motion. So we use theta. Again, we use theta for this case, instead of using S or X as the displacement. Okay. Again, small displacement. So we can use the assumption. Since the spring is subjected to an initial compression of XST. Okay, this is the additional information that you need to know. Okay, I read it until I finish. Then when the displacement X is bigger than XST, the spring exerts a force of F S equal to Kx minus Kx on the rod. Okay, what the meaning of the initial compression XST? So if you look at here, there is weight right here. We have weight, and right now the angle of this one is 0. Theta is equal to 0. But when there is weight right here, this spring has already compressed. Okay, the position of the spring is actually it's not its original length, so it's already compressed. Okay, so how to calculate the force right here is by considering the moment about this point. So you can calculate it by considering the weight. So right here also we have the reaction force Ry, Rx. So x and y is the direction. So since we use the pivot is at this point, so we can ignore the reaction force at that pivot. All right. So how to calculate? How to know x st or the force exerted at the beginning of the at the initial position, at the equilibrium position is, we can just we just consider that the spring has been compressed for x st distance. Okay, x st distance. So that is the force within the spring at the initial position. Okay, so when we push the bend rod upward, so now we can have we can calculate the force right here. Force because this is a compression, which is the force is acting this direction, and the tensile force or extension, call it tensile force, is acting this direction. Therefore, we this is the tensile force. That's why we minus the compression force. Hopefully you understand that. And in the kinematic diagram right here, we just need to calculate the mass, the acceleration of the mass. So in this case, we use acceleration AY. Maybe after this we will change it into theta. Why 5? Because 5 is the weight of the mass. Alright. So again, this is the similar diagram, just for reference. To obtain the standard form, FAY, again, AY is the acceleration in y direction, upward, which is in accordance with positive theta displacement. So again, acceleration should be positive according to the positive displacement. Now we can write down the equation of motion. After we consider the free body diagram and the kinetic diagram, we know what are the components involved in this case. So we can write down the equation of motion. Moment will be sum about point B. So point B is right here. So again, because we want to ignore the reaction force. Since theta is small, okay. So I complete this equation first. So mk is the moment which is against the motion of this direction, this one. So mk is in this direction. Alright. So we can replace the moment by considering the forces involved. So this is the forces involved. So actually the force that involved is Fs time 0.1 meter equal to we need to add additional force which is the weight. So the weight is in the same direction with the Fs, so we put 49.05 0.2 the length of this one. Okay, and this one is all equal to the acceleration -5 AY 0.2. Okay, why negative? Because we have consider that this is the anti-clockwise is equal to positive. Therefore, since the acceleration is clockwise, therefore it is negative. Alright. So this Fs is replaced with this one. Okay, and plus the weight equal to -5A 0.2. Alright, so this is the equation of motion that we can get. The second term on the left side, which is negative kx st 0.1, represent the moment created by the spring force which is necessary to hold the collar in equilibrium. So when we consider the weight and the compression in the spring, actually we can easily eliminate them, since this moment is equal and opposite to the moment created by the weight of the collar. These two terms cancel in the previous equation. Okay, so both of them are similar. I mean in this component, this one and this one is similar in value but different direction. Therefore we can cancel these two. Alright, so the outcome is this equation. Now we consider the kinematics. Kinematics mean the motion of the system. The position of the spring and the collar may be related to the angle theta. So we may replace the acceleration AY with theta. Okay, since theta is small, x is equal to 0.1 right here. S is equal to 0.1 meter time theta, and y is equal to 0.2 m time theta. So I finish this equation first. Okay, why we get this equation? X is equal to 0.1 m theta. Actually, this one, for example, okay, for example, we consider this triangle. This is theta. We want to measure this one. So we know this length, this is 0.2. So this length, we call it y. So y is actually sine 0.2 sine theta. But since for small displacement, sine theta is equal to theta, so we replace this one with theta alone. So that's why we get this formula and also this formula, these equations. Okay, so that is for displacement. Same goes with the acceleration. We use the same formula but with double dot. So this is with dot dot, this one is with dot dot. So when double dot is similar, so we just add double dot. So that's the angular acceleration, this one. Then we substitute this one into the equation 1. So equation 1, this one, right? So we have right here, we substitute that parameter with this one. So we get theta right here equal to negative theta double dot. So we can rearrange this equation. And we will get this simplified equation, because we want to arrange the equation to get the standard form. So this is the standard form. Now we compare with the formula that we have. You need to memorize this formula. The free vibration formula, this differential equation, and we will get the natural frequency, the value of the natural frequency, and we square root, and then we can get this value. This is the natural frequency, and straight away quickly we can get the period by using the same formula that we used before this. So I think that is the end of our lecture. So this 3 example is quite straightforward. Hopefully you understand, and later on I will give you the example which is more complex, so that you can practice yourself, and you can understand that how free vibration problem, how to solve the free vibration problems. So thank you very much for listening. Have a good day. Assalamualaikum and bye bye.